we are continuing with the volumes. First of all, I would like to inform you that I have received some of your works. Some of the people they did not perform the work seriously, others they have managed. So if you think you have done it in a wrong way, I think you will get what you have done, what you deserve. If you are given a work to do, please do it seriously, correct the data as required, and then report accordingly. So I have seen some of the reports are very poor, others they have managed to do something which is good, and I appreciate. But others, I don't know. I want to continue with the what you call the mass hole diagram. A mass hole diagram, I think for you, it is something new. Normally, a mass hole diagram is a graph. You can see from the first slide. It is a graph. And that graph, or it is a graph, we can say it is a curve. If we say it is a curve, is also the same. It is a curve or it is a graph that is used in route surveying for the purpose of visualizing or for the purpose of analyzing the cumulative volumes of earthworks that we need to move or that we need maybe to cut, to fill along the whole road project. Are you together, class? So let me repeat it again. Someone may ask you as an engineer, what is a mass hole diagram? In short, they state it as MHD. The MHD or the mass hole diagram is a curve or is a graphical representation used in route surveying for the purpose of visualizing or for the purpose of analyzing the earthwork or the cumulative earthwork volume that is needed along the whole project, either for cutting or either for filling. You as engineers to be, you should know that earthwork that we require or earthwork that we need for road projects can be executed in two forms. Either it is the earthwork that has been cut, that's what you call the cut material, or it is the earthwork that we need to bring to the project, what we used to call the filling material, the fill. That's why we used to have cut and fill or fill and cut. Okay, so this curve is of course a curve which is drawn whereby the x-axis, when I'm saying the x-axis is like the horizontal axis is representing the changes or is representing the linear information of the road project from the start till the end, and the vertical part of the curve, which is known as maybe y-axis is represented by the amount of earthwork, the volume, which is cumulative. You understand? So the volume is supposed to be cumulative. Of course, the mass hole diagram will be showing you the materials that will be moved and also, of course, the distance that is involved. And it will help you, for example, in planning earthwork, in estimating the costs, and optimizing, of course, the distribution of soil. So the diagram is plotted, as I have said, with the cumulative volume on the y-axis and the x-axis is representing the changes or it is representing the stationing or distances. Sometimes we can call it changes. We can call it maybe the distance or the stationing. So briefly, that's what is a mass hole diagram. So why do we need the mass hole diagram? Of course, I have already said we need the mass hole diagram because we may need to do what? First, we need to plan for the earthwork. So it is for earthwork planning. Second, we need the mass hole diagram because we want to estimate the involved costs. Three, we need the mass hole diagram because we want to optimize the soil's distribution. You know, along the project, from the start of the project to the end of the project, we need to be sure that the soil that we are cutting, we are not maybe losing it. What we cut, we may use it just for feeding, or what you have, we can make kind of a balance, so that the cut is used for the fill, and then maybe the excessive fill is what you can now dump. So a mass hole diagram is of course having some key characteristics because I have the way that I've told you. It has, if you can look on this first one, you can see you have the rising section, and we have also the steep slopes, the difference in the ordinates, horizontal line, and so on. For example, if you try to look on this curve, the rising section of the mass hole diagram, when you can see, for example, the rising section, what is the rising section? For example, from here, going here, this is rising. This is rising. This is rising. So the rising section of the mass hole diagram, it indicates that excavating exceeds fill. You understand? So it means excavation is going on. Whereas we have falls. For example, this part here, this is falling down. This is falling down. This is falling down. So falls will be indicating that fill is taking place. Fill is taking place. So what is the first characteristics is to see the rising section. If on your curve, the rising section is there, that is indicating that there is a cut. Meaning that cutting is taking place. Now, when you have the falling sections, this means that there is a filling activity that is taking place. Of course, when you look on the curve, for example, here, you can see sometimes slope of the curve is steep, or sometimes the slope of the curve is gentle, or sometimes the slope of the curve is flat. So steep slopes for the mass hole diagram, when you see that the slope of the curve is very steep, for rising, for example, so it means now there is a heavy cuts is taking place, or heavy fills is taking place. So you can have a steep slope which is rising, or you can have a steep slope which is falling. So we can note down that, so rising, this indicates cuts. Then falling section, this indicates fills. So if you have high rising, it means that there is a high cuts. If you have high falls, if the slope is very high, now it is a high fill, or sorry, if you have low rising and low falling, it means the volume of cuts and the volume of fills is of course also low, not too much. Then that's what we state in the bullet number two. In the bullet number two. So we have to make sure that the more the cut that we have, of course, the more the activity is required. For example, maybe we'll be needing heavy machines to cut, like bulldozers. And then you need also by that time a lot of trucks to carry the cut soil if you don't have anywhere to feed it. Then on the master hole diagram, we have another indication is that the difference in the ordinates between any 2 points indicates net excess of excavation over embankment and vice versa. So the difference, if we try to look the difference in the ordinates between any 2 points, that one will be indicating you that there is an excess of excavation or there is over embankment. Then another thing that we have to be maybe what I can inform you, the key components or the key characteristics of the mass curve. We have to say that, for example, that the terminology of excavation and the terminology of embankment. There is someone who is making a noise with his phone. I don't know who is that. Let us see who is that. Maybe as Mr. Siwoman Afis. Siwoman Afis, can you try to mute your microphone? Siwoman Afis. Siwoman Afis, you're making a noise. Yeah. Now let's go back to our presentation. As I have said, from today, we are learning, of course, the new terminologies which are related to the mass hole diagram. There is a terminology of excavation, and there is a terminology of embankment. Of course, excavation, it is also called as a cut. So we can also call it cut. We are cutting. Then when we talk of embankment, this also is related to the filling, to fill out. Okay? Then, if you try to look on the diagram, let's go back to the diagram so that you can see the characteristics. You can see that any horizontal line drawn to intersect the 2 points. Yeah, for example, if, for example, I draw a line here, let us say a line, you can see you have 0, 5,000, 10,000, 15,000 cubic meters. I forgot about this unit. This is cubic meters. Suppose I draw a line like this. This line will be intersecting this point and this point. So it means that that horizontal line that I have drawn, which is intersecting those 2 points within the same curve, it will indicate a balance of excavation and the filling. So it means if I draw a line like this, it means here I have the cut or the excavation, which is 5,000. Then here I have also a fill, which is 5,000. It is a balance. So it means the cut and the fill, they are equal. Okay? That is the characteristics number 4. So any line drawn on the curve, and that line, of course, is parallel to the x-axis, it will be indicating that there is a balance. So excavation equals to the equals to the fill. So it indicates a balance. Then again, if you look on this curve, there is a point of zero slope. Where is the point of zero slope here? If someone asks you, the point of zero slope, for example, is here. There is no slope. Here is zero. Here on the top, the point is zero. Zero slope. Here, this is zero slope. Here, this is zero slope. This point. So these points of zero slope represent points where roadway changes or goes from cut to field or from field to cut. Are you together, class? Look, I'm explaining the characteristics. You see this point here. This is what we call the point of zero slope. This is a point of zero slope. This is a point of zero slope. Here, how many points of zero slope do we have? 1, 2, 3, 4. So these points of zero slope will be indicating that we are now changing from cut to fill or from fill to cut. For example, at this point here, let's call this point here P1, P2, P3, P4. If this is P1, if the P1, you can see from this chainage coming up to here, this is a cut because it is rising. You know, yeah? When the curve is rising, it is a cut. So now this point is zero will be now indicating the change now from cut to the fill. Now from this point, we are now filling up to the point P2. From P2, now again, the cutting again starts. Cut. We are cutting till here. When we reach here, now we are changing again. So it means these points of zero slopes will be representing the changing, the change or where the roadway goes from cut to fill or from fill to cut. Okay? Are you together, class? Am I making sense? Do you get me? Okay. Then another point about the characteristics. The highest or the lowest point of the mass hole diagram represents the crossing points between the grade line or roadway level and the natural ground level. Okay? So the highest and the lowest point of the mass hole diagram represents the crossing points between the grade line, which is the roadway level, and the natural ground level. For example, the lowest points, I think the lowest point here is this. Okay, this is the lowest point. This is the highest point on this curve. Okay, so now this highest point will be representing, of course, the maximum, the grade line. And this will be representing, of course, so of course this goes with respect to the natural ground level. Okay, so and this is what we can see here. Those are the characteristics that I was showing you here. Sorry, I think I did not show you the slide. Yeah, the slide is here. So actually, you know, I was explaining these characteristics on this diagram using, of course, the previous diagram. So let me repeat it again for the people who did not understand properly. Let me repeat it again. Sorry. Class, please look at this diagram. This diagram has some rising and some falling section. For example, from here to here is rising. From here to here is rising. From here to here is rising. So where we see the rising section, This shows that cutting activities is taking place. Where we see this falling, this means feeding activities are taking place. Okay, so on master diagram, rising means cut is there and the falling fields are there. Then another terminology that you can use is that excavation are also called cuts, and then fields are also known as embankments. We have also discussed, that was characteristic number one. Characteristic number two, we have seen that the slope, if the rising section slope is high, so heavy activity is taking place. We have seen that if also any line is drawn, for example, here or here, it means horizontally parallel to the x-axis, it means that it indicates a balance. It indicates a balance. And we have also said that there's a point of zero slope here, there, there, there. These points of zero slope indicates that we are changing from cut to fill or changing from fill to cut. So these are the characteristics of the Maslow diagram for the moment. Now, another good question is that someone may ask you, what does the mass diagram tells you or is telling you, for example? Normally, I have already said in the three stages previously, the mass diagram, first of all, is for planning purpose. It is for planning for what? Planning for the earthwork. Because when we talk of the earthwork, we need either the cutting of the earth or the filling of the earth. So by having the mass diagram, you will be able to of course, indicate where the cuts are taking place and where the fill are taking place. Then by the mass diagram, you can be able to estimate the cost. Maybe cutting is this, maybe, normally cutting and the filling is not quoted as far as the money is concerned in the same manner. So I think you know that filling activities are costly. Once you will be required to deal with the road construction project and you will be required to fill, please guys, pay attention. Fill, you need to raise up the road. You need to cross, for example, a wetland. You need to cross like some section which is very low, and then you want to raise it up. If you want to raise it up, you will fill. So filling, my friend, is very costly because you need to compact. You need to set a good suitable materials which will resist and so on and so on. So filling, in my projects, most of the time when I'm dealing with the construction project, I always fear, I am telling you, I always fear to have too much fill. Because they will be costing too much of the project. So fill. So then, if you have now the master diagram, you can see if you have too much fill, now you know how the cost is. Then, by the master diagram, you of course optimize or to distribute the soil economically. Optimize, so use the soil economically. Distribute the soil economically along the whole road project. Are you together, guys? So, of course, the mass diagram will determine, of course, these are some of the new terminologies, what you call the haul distance, average haul, free haul, overhaul. The whole distance, normally, the whole distance, the whole is the transportation. The whole is the transportation of material from its original position to its final location. So whole. How? Because if the hole is too much, now the project will be costly. Of course, for example, when you're dealing with the feed, then um, the average hole, it means like it's just like acceptable, acceptable. You can have overhaul, which is beyond the hole. Then free hole. Free hole means within that distance, some costs will not be charged. Some costs will not be charged. So let me look for another diagram which has been done by our students. Then I want to share it with you so that you can have a look on it. Just wait for like just like 1 minute. I look for that one, then I share it with you. Okay, I think you can see now the diagram. Sorry, you can see the table here that I'm showing you. Uh, Practically, this table is the general table which is used when we are dealing with the mass hole diagram computation. Mass hole diagram computation. If you look, you remember I told you that the mass hole diagram is a diagram which is drawn with the x and the y axis. On the x-axis, we are putting the changes or we are putting the distances. So you can see here you have the changes 0, 100, 200, 300, 400. So this is like a road section of around 600 meters. Then for that particular road, normally the project from the change 0, of course, it is the start. That's why you say the cumulative volumes is 0. That's why it is 0. Now, when you go to 100 meters, so it means from 0 up to 100 here, because we have the volume of cut. You see? So we are cutting the soil. Cutting the soil. That's why the cumulative volume will be 22,200. Sorry, I think here there was a mistake. 22,275. So he wrote 57. So he interchanged these values. So, but this value is supposed to be here. And then we continue from 100 up to 200 meter. We are still also cutting. So between this section, between 100, the change of 100 meter and 200, we cut the volume of 13,902. So which means now when we shall reach this 200, now the volume will be cumulative. You know the mass flow diagram, it will be giving us the information about the cumulative volume. You remember by definition, so it is to analyze the cumulative volumes. So we'll be having this 13,902 plus this. And then it becomes 36,177. This is cumulative. So then from 300 up to 400, we are filling. You see, we are filling. We are filling. How much? 2,000. And then you should know that sometimes the materials have some properties. Of course, that's why we say maybe let's go in the normal practice class. If you dig a hole of 1 by 1 meter, so let us say you have 1 meter width, 1 meter length, and then 1 meter deep. After digging, if now it comes to the backfilling, you either have excessive soil You see, because the soil has, of course, uh, has gone what you call some kind of expansion. Depending on the type of the soil will expand. And then if you try to fill, it may not fit there. Or if, or sometimes if you fill, now the soil becomes less. Normally we used to say that, for example, like clay soils, once you excavate, the backfill becomes too much. But rocky soils, once you excavate, you backfill, then the soil becomes less. So that's what we have the characteristics of bulking, what you call bulking, and shrinking. You understand? We shall explain it later on. So here you can see in this exercise that has been given to the students, the cut materials, there was no problem with the with the bulking, with the expansion, if you can say. So what you excavate is what it remains. This it was just an assumption. But when it comes to the fill, you do not fill what you have. You have to fill too much because you fill, then the soil will shrink, will reduce the volume. So that's why we here we use the shrinking factor, the shrink volume. So the shrink factor it was 10%. So if you want to fill this much, now you have also to add again 10% for taking into account the shrinkage. That's why you have this plus this. Then you have 2,494. Then from, you can see this is from 300 to 400, then from 400 to 500, you have this. From 500 to 600, you have this. Then from 600, yeah, between, you have 900. So actually this here, it shows you that the shrinking was applied because the fill material was having the characteristics of reducing its volume. Then you can see here, you can see now here, this has become negatives and this has become positive. I did not want to tell you this one before we started. So what you have to know is that by the mass hole diagram, all cuts, I think when I'm saying cut, you understand what I mean. When I mean cut is like excavations. All excavations or all cuts are considered to be positive volumes. Are you together, class? In a root surveying, all cuts, all excavations, volumes are treated to be positive volumes with a plus sign. Then all fill materials, how do we call again the fill materials? Fill materials are also known as embankments. Fill materials or embankments are treated as negative volumes. Why do we treat them as negative volumes? It is because we need them to be brought on the site. So we are lacking. But once you cut, you of course physically you have something. But when you need to fill, you need to bring. That's why all the fields, all the filling materials, all embankments will be treated by having a negative value. So for example, for our project, if you try to draw, so we are going to draw, so that's why you see this last column, cumulative volumes, you have 0, so we are going to add. You add. So now here we have 36,177. Now we minus this, we have this minus this, now I have this minus this, now I have this minus this, now we have this. So now we are going now to plot this chainage column. This is along x-axis, this is along y-axis, and then we shall produce something which looks like this. This is an example of what been produced by our students. But what I can also say is that these students, maybe they have managed to draw the curve, but the curve is not proper because uh, it should be a curve which is smooth. So the curve was somehow like lines joined by, you see, like straight lines. That's why they cannot get all the marks. Maybe they got around like maybe 6.5 out of 10, 6.5 out of 10. Because this was supposed to be a curve. This is supposed to be normally a curve. A curve. Meaning that from 0, coming to 100, coming to 200, you can see this, all this section from here, coming up to here, this is indicating the what? The cut is taking place. This is the point with the 0 slope, remember. Because now we are changing, now you are coming here with the feed, the feed, the feed, the feed, the feed, the feed, till the end of the project. Then you can see at the end of the project, we have something. This is a minus 2,500, meaning that with this project, we are having something we need to borrow. We need to bring some materials because what we have cut here, taking into account the shrinkage, we can use it. We can use it. But when we reach here, you can see now from here, now we have now to bring. So normally, uh, the volumes above this line, the volumes above these lines, these are what is available in practice. And here, this one you can see we are missing. So we need to bring the materials. So this is an example that I want to show you and I want to share it with you. Now, let's we have discussed. Sorry. Yeah. So now let us see some of the key terminologies or key components. If you want, you can write it down. The key components of a mass hole diagram. Key components of a mass hole diagram. Key components of the mass hole diagram. I'm trying to look for the I'm looking for the notes. Yeah. There's something that we have to note down during the definitions. And then if you could take maybe, let me see if I can put a slide here. Then I'll be writing them. Okay. So there are some key, key components of the mass hole diagram. So I have already said the first key component of the mass hole diagram is the rising and the falling sections. Falling sections. Second, second, the key components. Let me try to increase the size. I think it's small. Yeah, maybe this one. The second key component of the mass hole diagram is the curve itself. Curve. Another key component of the master diagram is I have said, what you call the balance line. Balance line. Another key component of the master diagram, of course, is the cuts and the fills, or we say excavations and the excavations and the embankments and the embankments. Another key components of the master diagram are the peaks and the valleys. Peaks and the valleys. Valleys. Points. And then we have also what we call surplus, 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 and deficit. Then we shall also talk about what we call borrow and the waste. Do we have a borrow? We have a waste. We have a borrow or we have a waste. So these are the key components of the master diagram you as engineers to have it in your mind. Now, I'm going to explain one by one. Please pay attention. Yeah, top and then I think here I have to write. Okay, copy, paste. Key components of MHD. Key components of MHD. To use the color. Oh, what is this? Okay, no problem. So, I think these ones, most of these terminologies, key components, I have already discussed, but I want to highlight them again for you to understand and for you to know it. And the falling sections, rising and the falling sections. Another diagram, maybe this one. This is rising, this is a rising, this is rising, this is falling, falling. Okay? So, the rising and the falling, of course, the rising will be indicating that a cut is taking place. Okay, rising means rising section indicates that cut place along the road project. Because this is a small segment of 600 meters. I will give you an example, for example, of a 10 kilometers or maybe 5 kilometers that you will do yourself, and then you draw the master diagram. Then try to understand. So let me open. Can you see the slide now? Can you see the slide? Okay, fine, huh? When to come back here? Sometimes you may come back to the slide, then a student cannot see. Now let's go to the curve. The curve itself. How do we produce the curve? First of all, the mass hole diagram is made up of a curve. That curve should be a continuous line, a continuous smooth line. First of all, it should be a continuous smooth line to represent the cumulative volume of earthwork. Do you understand? So the curve of the mass hole diagram is a continuous smooth line that represents the cumulative volume of earthwork along the project. And that line will be giving you the information, of course, at each point. For example, if we come back to this curve, of course, this example was done by students. You can see, of course, first of all, the curve is not smooth, which means that the marks we are not very much. I awarded him a very 6.5 out of 10, I think. You can see maybe if we are, for example, at each point, for example, at 100, you have the cumulative volume. What's the cumulative volume at 100? You can come and see. You see, at 100 meter, the cumulative volume is 22,275 cubic meters. For example, here, how do you think is this one? Because this is 100, this is 200, this is 150, this is 175. For example, at 175 meter, the cumulative volume is this. Can you see? It is this much. At 200 meter, the cumulative volume is this. Okay. But because this is I think this is the highest volume, but this also is the cumulative volume. The volume is cumulative, but you can see the curve now is going down, which means that now some filling activities have started. The total volume that you have cut up to 200 meter, from 200 going up to 300 meters, we are starting to fill, till we reach it. You can see from 0 up to 500 meters. What you have cut from here up to here, from 200 up to 500, we have all filled. Now we are remaining with no soil. Then from here, we need now to borrow. You understand? That's why there is a terminology of borrowing. Okay? Sawa. So the curve, as I've said, the curve will be helping us as a continuous smooth line to represent the cumulative volume of earthwork along the whole project. Now, let's look at what you call balance line. Balance line. What is a balance line? A balance line, of course, as I have said, it is a horizontal line which is drawn parallel to the x-axis, and that horizontal line, of course, it will be cutting, it will be passing through 2 points. Passing through 2 points. Balancing line. Passing through 2 points to represent the cumulative cuts and the fill volumes. And in that particular place, the cuts and the volumes are equal. You understand? So a balance line is a line representing the points where cumulative cuts and the fill volumes are equal. Let us see on this example. You can see this balance line, for example, JK. Can you see? JK can be treated as a balance line. HI can be presented as a balance line. EF can be presented by a balance line. Maybe from here, no, this is not this is already the challenge. So from here, it means at this point J, you see the volume of earthwork. How much is it? It is here. I think it is around maybe 15,000, maybe 16,000. Okay, 16,000, but of what? Because we are in the section of cuts. This point J is having the same value with the point of K, but in different types of volumes. At K, we'll be having the fields, because you see, it is 16,000, but fields. So this will be cut, this will be field. This will be cut, this will be field. Cut and field. So this balance line will be representing the points where we have equal volumes. Equal volumes, one is a cut, another one is a field. Okay? Now let's go to another, I think cuts and the fields, excavation, I think this one. Of course, balance line in the cuts and the field, I all explained together. I showed you the balance line, and then I showed you the cuts and the field. So they came both at the same time. Then peaks and the valleys. Peaks and the valleys points. If we try to use this diagram, here, this one, this is a peak, this is a peak, and this is a peak. This is a valley, this is a valley. Okay. You understand? Valley, valley, peak, peak. So peaks in the curve will be indicating that we are changing from cut to fill. Of course, when I'm here, from here up to here, I was cutting. Now I'm changing to the fill. Here also. This is a cut here. Then I go to fill. But when I come here, when you go to valleys, it indicates a change from fill to cut. You understand, class? So peaks will be indicating the change from cut to fill. Valleys will be indicating the change from fill to cut. From fill to cut. Okay? So if I use, for example, this diagram of the students, I think here we're having only one peak, which is this, which is a C. We don't have valley here. We don't have valley, but you have one peak. Our peak is a C. We are changing from this cut to the fill. You can see, if you have such a project, you will know that from maybe 0 up to 200, you will need maybe a bulldozer to cut and trucks to transport what you have cut. But from this one, going there, there is no need of a bulldozer. Maybe you need like a compactor and a grader to display what you have cut from here in this part. Okay. Again, we have another terminology which is about surplus and deficit. Surplus and deficit. Surplus. When do we say there is a surplus? When do we say there is a deficit? We talk of deficit when you have a negative difference. That's deficit. Deficit means negative difference. Deficit, this is a negative difference. Then we say surplus material when you have a positive difference. So we can say surplus is by plus sign, then deficit by negative. So where do we call surplus and deficit? As I have said, it is the difference in the mass hole value between 2 points. 2 points. if there is a surplus or if there is a deficit. For example, let us see in the diagram. Let us try to use this diagram of the students, and let us say maybe these 2 points. From here up to here, these are 2 points here up to here. There is nothing. There's no, the cost is equal to 0. They're both equal. Here, the difference, because here we have 0 and here we have 0. And then if, for example, we have this point and let's see, this point and this one, this point and this one, sorry. We can put, we have A, B, we have J, K, maybe L. Let us put maybe L here, L and the M. So if you have point here, L and the M, these 2 points, L and the M. So you can see from L to M, L, we have 0. M, we have this, which is how much? Minus 2,500. So here we have what? We have a deficit. So we have 0 minus 2,500. There is a deficit in this particular case. For example, let us consider the points here. This point E and the point E, is it E? I think this is I. E, what is the volume? What's the cumulative volume? E, the volume is 33,000. No? I can see 33,689, for example, cubic meters. Then this is A, E, and this is the I. I, how much is it? I think here it is maybe 17,000. 17,000. You can see if we take this minus this, we are having a positive difference. The positive difference means there is a surplus. We still have some materials. We still have some materials to distribute to the project. But between this point and this one here and this one here, we don't have material, but we need to break. There is a deficit. Then let's come back. Is what you call the borrow and the waste. Borrow and the waste. What is borrow and the waste? We talk of a borrow when you have a negative value, when you have, of course, a deficit. And you talk of waste when you have a positive value. In some project, it may happen. You end up by having at the end some materials which is remaining, and that is treated as a waste. So we shall call a we shall call the borrow materials when there is a negative value at the end of the diagram. We shall call a borrow material when there is a negative value at the end of the diagram. Of course, normally that is needed to execute a fill. This is an example that you can have here. You can see from at the end of the project, you can see at 600 meter, you still have a negative value, which is 2,500. So this is a borrow. We need to bring the materials of equal to this amount of volume to bring the project up to this level. Then, if for example, instead of having this, maybe if you have something like coming here and then maybe go up, if it goes up, now we'll be having something here above, and that will be treated as a waste. And that waste is when a positive value at the end of the mass hole diagram is there. So a positive value at the end means there is waste material that will not be used. Okay, so you need now to remove that soil and then you go and dump it somewhere. Okay, are you together, class? So let us have a short break. Let us have a short break of 5 minutes only. 5 minutes.